We're looking at number 1. So the first order of business, if you want to find out the frequency of 410 nanometer light, is to convert your nanometers to meters, because it has to be in meters to use our speed of light formula. And at this point, we know that the speed of light is 2.998 times 10 to the 8th meters per second. We now know our wavelength, which goes right in there, and then we can solve for our frequency. And so I get 7.31 times 10 to the 14th, 1 over seconds, or of course you could do hertz if you wanted to. And remember to check for sig figs. We have plenty of sig figs here, so it looks like that's going to be the limiter, although I didn't check. Let's see, 410. Oh no, there's no decimal point. So I actually should not have that 1 on there. Oop, I can't erase it, but in any case, I got to get rid of the 1. So it should be to 2 sig figs. To find the energy, of course, we can convert this to energy using the photon formula. So where H is Planck's constant, and I'll let you look that up on your AP Chemistry and Equations constant sheet, and then it's really just multiplying the two of them together. And I get 4.8 times 10 to the minus 19th joules. The answer is going to be in joules there because Planck's constant is joules times seconds. In part B, so this is B, and this was A. In part B, all they want to know is how much it would take to excite a mole of those atoms. Well, if this is the energy of one single photon going to one atom, then if you were going to do a mole of them, obviously it would be many times that amount. So it would be 4.8 times 10 to the minus 19th joules, and then we got to multiply that times 6.022 times 10 to the 23rd atoms in a mole. And that should give you how much energy you'll get for all of them together. I get 291681.9, but that's in joules, and it wants it in kilojoules, so we've got to move it 3 decimal places over. So it looks like it could be about 292 kilojoules. I got to check my sig figs. It came from all this stuff up above, which had 2 sig figs, 2 sig figs. So I probably need 2 sig figs, so 290 kilojoules should be the final answer. And then the answer C, I'm not going to write it out here because I have kind of limited room, but they want to know if this light is, if it's barely visible to the human eye, predict whether it has higher or lower energy than visible light. And we remember that the visible light spectrum goes from about 400 nanometers at the high energy end, and that's supposed to be NM, and to about 700 nanometers at the low energy end. And so this is 410, so you notice that would imply that it's just inside the visible amount, but we're right on the border. But since this is the high energy end, we're going to say that the energy should be just higher than visible light. We're somewhere down here on that slightly higher energy end. But I want you to write out an actual explanation of that. I just don't have room to do it here. In number 2, which of the following electron configurations represents an excited state electron configuration? And the answer turns out to be the bottom one. And we can draw out the filling diagram to see why. So here I've got it drawn out exactly as it's listed in the electron configuration. So 1s2, 2s2, 2p5, and that's where we see the 5 is not full. There's a hole there, which tells you that there should be an electron there. Where did it go? Well, it got boosted up to the top by light. And so it will eventually fall back down, and probably this 4s one is going to fall back down and fill in the hole. Now you might wonder, well, can a 3d one fall down there? And of course, but then that would create a hole and the 4s would fill its place. So effectively the 4s will fall down. So our rewritten electron configuration would simply be 1s2, 2s2, 2p6 to recomplete that one, 3s2, 3p6, and now there will be nothing, when it falls back down in there, there will be nothing in the 4s, so we don't need to write it. So that'll be the answer to A. In B, explain what event might occur to get the atom in an excited state electron configuration. So I'm not going to write it out because of limited time, but you definitely should. The event that will occur is that the electron, which was originally in this 2p, will get struck by light, and we might want to say absorbs light, which will cause it to have an increase in energy. That's an endothermic process, and that'll get it to a much higher energy state. And then in C, what event occurs as the electron relaxes? The event that occurs as it relaxes and falls back down, of course, is the emission of light. And that's a great word, emission of light. Maybe one that we haven't said in class, but you definitely should know. So that's the event for the second one. And when you write it out, I want whole sentence explanations as if you're taking the AP test. Let's look at 3. 3A, draw the shorthand electron configuration of potassium. Now that's pretty simple. Since it's shorthand, all we got to do is do the very last row, and potassium is in the 4th period. Stop calling them rows, we'll start calling them periods. The 4th period of the periodic table, and the first area of that period is the S area. So it's going to be a 4s, and since potassium is the very first element, it's going to be 4s1. You remember we have to do the entire last row in a shorthand electron configuration. But we can abbreviate all the others by the last noble gas before we got to the 4th row, and that was argon. So it's going to be argon in this spot. B, draw the complete filling diagram for potassium. And it's going to be, if you're going to do a complete one, then it's going to be something that looks a little bit like this. Alright, there we go. And yes, you need to be able to do this solely from the periodic table. If you're having troubles doing that, you definitely need to come in and see me during academic support to find out how to do that. And then in B, draw the complete filling, or we just did B, so that's over there. C, draw the complete Bohr model for potassium. And the complete Bohr model, we'd have a center ring, and we go out like this. And potassium's going to have, it looks like its atomic number is 19, so it's going to have 19 electrons. So there's 2 in the inside shell, there's 8 in the next shell. 1, 2, 3, 4, 5, 6, 7, 8. So we've used 10 and we have 9 left to go. And yes, you can put those remaining 9 on the 3rd shell because it can hold up to 18. 2, 3, 4, 5, 6, 7, 8, 9. And there we go. And then in D, circle the highest energy electron in each of the previous models. Well, you could choose anything in this 3rd ring. You could choose obviously the 4s orbital, and you would circle that one as well since the superscript indicates the electron. And then let's do a new page here. And then let's see, E, predict the most common ion formed by potassium and explain why it forms. So let's take a stab at this. In E, we think that the most common ion is going to be potassium plus 1. Because we've been using it all year, there should be no doubt about that. And then we got to come up with an explanation. So here's what I came up with. The most common ion is potassium plus 1. Neutral potassium loses 1 electron to become isoelectronic with argon. This forms a stable full valence shell electron arrangement. Now you notice I didn't say because noble gases just happen to be stable. That's an observation. The reason is that a full valence shell happens to be a stable electron arrangement or configuration. You don't have to say arrangement. That's the key phrase there. And then F wants to know if potassium will be attracted to a magnetic field. Remember that what it's really asking you is it's asking you if magnesium is diamagnetic or paramagnetic. And for that, it'd be best to go back to your electron configuration, which I can't really do at the moment. But you'll notice that potassium in the 4s orbital, it does have an unpaired electron, so it is paramagnetic. And so the answer is yes, it most definitely would be attracted to a magnetic field because it has an unpaired electron. You remember that the atoms that have all paired electrons are the ones that have no ability to be attracted to a magnetic field at all. And so I'm not going to write this out, but you definitely want to write more than just what I wrote here.